These are the voyages of the statistician, our continuing 5-month mission to seek out forms of error and to destroy bias within the universe. Oh, I shouldn't be so evil. I'm wearing my pink shirt. Whoa! This is my Happy Valentine's Day shirt. So it's supposed to be a loving shirt instead of a destroy the universe shirt. Let's talk about the normal distribution. This is critically important. We are going to use the ideas of this lesson all semester long. So it's really important that you can't see because there's a glare. It says normal distribution. The normal name is because this is normally what is used for a lot of situations. It's also called the bell curve. It's called the bell curve because in the Disney movie, Princess Belle wears a dress just like that. Okay, that's not actually true. My wife says that if I lie out in these videos, there will be a special place reserved just for statisticians in the afterlife. Every normal distribution looks like this. No matter where they're centered, no matter how fat or spread out they are, they all have the same curvature to it. And if I was a perfect artist, it would have that nice perfect curvature. You can graph e to the negative x squared if you want to see it on your calculator. So where this middle is, we're going to call that mu. That is the mean. It's also the median, but we're interested in the mean. So mu is what we call the mean. This guy right here is a measure of how spread out it is. It's the point where it stops curving down and starts curving out, like on a roller coaster. In calculus, they call that the inflection point. From the mean out to that point is our sigma. That's our standard deviation. And that's why we've cared so much about calculating standard deviation up to this point. Now, the notation that we use is we say capital N for normal, and then you put the mu, comma, and we put sigma squared. Sigma squared is the variance. On the picture, it's sigma. The difference is the picture likes to use sigma because you can see that distance there. Sigma squared doesn't show up on the picture well at all. But mathematically, sigma squared is going to show up a lot. And so the notation uses sigma squared here. So let's do an example. I want this exact curve, and we're going to put some numbers to it. So because this is a smart board, watch how I can copy and paste. So we have here the exact same curve, but we're going to use a specific example with how much sleep do college students get on average. Let's pretend that on average you get 8 hours of sleep. Why? Because that's what science says is healthy for you. So I'm sure you all get 8 hours of sleep. So 8 hours is my mean. For my standard deviation, I'm going to put 2 squared. The reason for putting the squared instead of writing 4 is it helps emphasize 2 is what goes right there. So 8 hours of sleep is reasonable. Is it possible that you might be getting 6 hours of sleep? Where would 6 hours of sleep land on this graph? We have 8 hours right here. This is a distance of 2 hours, so 10 is right there. If I go back 2, there's a distance of 6 hours. So yeah, getting 6 hours of sleep, that's perfectly reasonable. Could you be getting 4 hours of sleep? Well, that lands 2 standard deviations back. It's rare, but it does happen. This is college. Could it be that you're getting 2 hours of sleep? Very, very rare. If you're doing this all the time, that's a problem. Now, technically, the normal distribution continues on. In fact, it would even go to the negatives because the math doesn't care that you can't sleep a negative amount of hours, although I feel like I've done that sometimes. And technically, it goes on forever. You could sleep 30 hours. Actually, you probably could. That might not be unrealistic. But this little range right here is enough for us to see what's likely for probabilities. Now, if you're thinking to yourself, this doesn't look right because getting 4 hours of sleep is very common. Great, what you're telling me is you think that this is wrong, and one of the things we're going to get to in the future is can we test whether we agree with these and whether these are right. Now let's try a couple probability statements, and we're not going to solve them mathematically yet, just with a picture. What's the probability of getting less than 6 hours of sleep? What we would do is we would go from 6, and we would fill in that area right there. If you want to actually calculate that, you need to integrate e to the negative x squared. Don't try it. It's going to give you a headache, okay? Just deal with pictures right now. That's what it would look like. Let's try something totally different. What's the probability of getting less than 6 hours of sleep or equal to 6 hours of sleep? If you look at the picture, it's going to make sense when I tell you it's the same answer. This is continuous data. What's the probability that you would get 6.0000000 hours of sleep? The video's backwards, right? It looks like I'm going higher on them. To me, it looks, okay, 6.0000. The answer is there's no chance of that because this is continuous data. You can't get that. So whether I include the 6 or not actually does not matter at all. You'll get the same answer here and here. What if the question was, what's the probability that you sleep more than 7.5432 hours? Well, what we're going to do is we're going to figure out where 7.5432 lands on here. Okay, a standard deviation is 2, so it's about half a standard deviation. That's 7. 7.5 would be here. 7.54 would be right about there. So that's where my line goes, and I would shade in all of this area for the probability. What's it going to be? 55%, 60%. You can kind of eyeball it if you're a really good artist. What if we wanted the probability of sleeping between 4 and 9 hours? Great, it's easy to do with the picture. Right there is 4, right there is 9. I really encourage you to always draw the picture on these things. You should be able to get an idea in your head of what the answer is even before we start doing the math. Looking at that, I can eyeball it as 60%. So if you did this and you got an answer of 40%, you'd say, hold on, maybe I calculated the wrong areas. And that's one way you can help check yourself.